Hello everyone, my name is Mikołaj Kuska. I'm from Polish Astrobiology Society. Welcome all of you on our next lecture during last days. Our next speaker is Professor Sara Seager from Massachusetts Institute of Technology. To be honest, I'm very happy to be your chair because last year I've been the chair of Janusz Pętkowski lecture, and Sarah's lecture is a continuation of the same story, but with new results. Sarah, the floor is yours.
Thank you so much. Can you hear me okay? I'm here to tell you.
Yes, we can hear you.
Thank you. I'm here to tell you about the search for signs of life beyond Earth. And this story about the search for life begins billions of years ago, when here on our planet Earth, something amazing happened. A simple single-celled bacteria, cyanobacteria, figured out how to harness energy from our environment, that is photosynthesis, and in the process generated oxygen gas as a waste product. What is so amazing about this is over time, oxygen came to fill our Earth's atmosphere to 20% by volume. But without life, without plants and vegetation and photosynthetic bacteria, there would be no oxygen in our atmosphere. It's like spraying a perfume bottle. If you spray it, you can smell the perfume, but eventually the perfume reacts with the air and the smell goes away. You would have to be continually pumping in perfume in order to get that smell to remain in the air. So the point is that oxygen is so reactive. Without being continually pumped into the atmosphere by life, our planet Earth would have virtually no oxygen. So, about 100 years ago, an astronomer, James Jeans, wrote a textbook. And in that book, he had a couple of paragraphs on this topic. I've copied a paragraph here. And he pointed out this fact that we should have oxygen. Oxygen is a sign of life on our atmosphere. And ever since then, we astronomers have been wanting to find signs of life elsewhere. But interestingly, on Earth, we've only had 20% oxygen by volume in our atmosphere for about 1 billion years. And the other few billion years, we didn't have enough to be remotely detected. So in exoplanet astronomy, we're constantly asking ourselves, what kind of gases other than oxygen should we look for? And today we actually have quite a giant list of gases. We have phosphine and ammonia and methane under the right circumstances could be a sign of life on a planet beyond Earth. And we have lots of more molecules of interest. So it turns out that it's not just exoplanets where the search for signs of life is going, but actually much closer to home, our sister planet Venus, which often shines brightly in the morning or evening sky, has some very unusual gases in the atmosphere. And this slide is credit to Janusz Pętkowski, and you can read his lead author review article about all of the strange gases that are detected, or even if they're controversial, reported to be detected in the Venus atmosphere. And I'll just kind of let you browse this slide while I talk to it. But many of these gases shouldn't be there. Just like oxygen in our Earth's atmosphere, many of these gases, according to chemistry, equilibrium chemistry, shouldn't be present in the atmosphere. And this is one reason why people keep an old idea alive that perhaps there's life in the Venus atmosphere. So gases that don't belong, that are far out of chemical equilibrium, are often used as a very suggestive sign of life beyond Earth. Venus has a lot of them. So today, I'm going to first talk about Venus clouds as a possible habitat for life. Then I'm going to move on to space missions. I'm going to update you on our series of private-public partnership missions to go to Venus and look for complex molecules in the search for signs of life beyond Earth. Third, I have a brand new topic. I can't wait to tell you about it. So let's talk about Venus. Many of you already know that Venus at its surface is too hot for life. Venus has a massive carbon dioxide greenhouse atmosphere, and it's just so hot at the surface, we really can't imagine life living on the surface like it does here on Earth. But just like on Earth, if you hike up a mountain or go in an airplane, it gets colder and colder the further above the surface you are. And so too on Venus. 50 kilometers above the surface of Venus, it's the right temperature for life. And 50 kilometers above, it's actually cloudy, very cloudy. The clouds on Venus are always present. They're vertically very thick, and they're surrounding the planet at all times. We have life in our clouds. On Earth, bacteria is swept up from the surface and gets trapped in the clouds for a week or so before being rained back down. All of this is why, half a century ago, Carl Sagan first proposed that perhaps there's life in the Venus clouds. Well, here's a schematic about Venus showing you kilometers on the left and on the right, temperature and pressure. And we've used these dashed lines to show you where the temperate zone is, where the temperature is just right for life. But the problem with Venus is that the clouds aren't made of water, a very friendly to life substance, but they're made of concentrated sulfuric acid. Concentrated sulfuric acid kills all of our life. It's a really, really destructive chemical. I'm not sure how many of you even know what sulfuric acid is, but it is so dangerous. It will like burn a hole in your clothes, in your skin instantly. And just to convey to you just how destructive sulfuric acid is, I have prepared a video. And in this video, that's me, Professor Seager, in my laboratory at MIT. On the one side, you can see like a regular image. On the other side, you see an infrared camera, and it tells you the temperature in degrees Celsius. On the right, I'm showing you a cartoon of a DNA molecule. So our DNA has different parts to it. There's the latter part, the DNA nucleic acid bases, ACGT, and there's a sugar phosphate backbone. So this video is showing you what happens to our life in sulfuric acid, not from putting life in sulfuric acid, but we're not putting life, we're not putting DNA, but we're putting in sugar because our DNA has sugar in it. So sugar is a proxy for DNA, is a proxy for life. Ready? Here's the video. It's just the kind of sugar you would have in your kitchen. And that concentrated sulfuric acid requires a lot of safety to use, those gloves and glasses and everything else. This movie is sped up 2.5 times. What's happening? It's already reacting, turning dark brown. And in the thermal infrared, you can see it heating up rapidly. Wow. Look at that. It's not good for life. This sugar is getting dehydrated. What's coming off of it is steam, essentially water, hot water, vapor. And sulfur dioxide is also coming off, and it is nasty. It is as it looks. It's just scary to think about sugar as a proxy for DNA, as a proxy for life. No wonder people don't think life can survive in sulfuric acid. No wonder people don't think that life could survive in the clouds of Venus. So, wow. Even despite all of this, a small group of people has kept the idea of life in concentrated sulfuric acid, the possibility of life in the clouds of Venus, alive for many, many years, decades actually. And how I got involved with this work, it's really kind of too long of a story for me to capture today. But let's just say I started out as an exoplanet astronomer and working on search for signs of life beyond Earth. In our computer, myself, Janusz Petkowski, and others, we came across many interesting gases, including phosphine. Phosphine as a potential sign of life. We teamed up with a group from the UK led by Professor Jane Greaves. And long story short, we reported a detection of phosphine gas on Venus. And we showed with 100 pages of hard work in chemistry that we couldn't explain the presence of phosphine by any known chemistry. Could be unknown chemistry, could be life. Nonetheless, that is how I got involved in laboratory chemistry. So normally you would be like, wow, okay, forget about life on Venus. Our DNA is just, wow, destroyed so rapidly. But we didn't take that attitude. We decided to explore, because honestly, the number of planets, the number of solar system bodies that we can explore, we don't want to lose any opportunity. We want to be able to take full advantage of what's nearby. So we started working in the laboratory. And what is so fascinating is that although our DNA is unstable, because the sugar phosphate backbone is unstable, it turns out there is one part of our DNA that is stable. And this is the nucleic acid bases, ACGT, adenine, cytosine, thymine, guanine. These are actually stable in concentrated sulfuric acid for more than 1 year. I'm showing you like a very technical image of the data, which I'm not going to explain to you, but I left the references in case you're a chemist and you want to read about our NMR, nuclear magnetic resonance spectroscopy, that we use as evidence to show it's stable. What in fact we set out to do was to construct a DNA-like molecule. Not our DNA, but swapping out parts. Because we're trying to show that complex molecules, even up to informational containing polymers, could be stable and could exist in the Venus atmosphere. We're certainly not trying to say that there is life in the Venus atmosphere. We're trying to motivate space missions to Venus. Now, we do have a milestone, thanks to Janusz Petkowski, and that is not DNA, but a related molecule used synthetically called PNA, peptide nucleic acid, where the usual sugar phosphate backbone is replaced by a glycine-related backbone that is stable in concentrated sulfuric acid. This is a huge milestone. We're extremely proud of this step. We still have a ways to go. We have to find something that is more robust against temperature and demonstrate that single strands can come together in a helix. I know that Janusz Petkowski talked about this last time. We have a lot of data, so much. I mean, what I have just mentioned is literally just the tip of the iceberg in organic chemistry and concentrated sulfuric acid. We have a lot of laboratory studies ongoing. We've been recruiting team members to work on theoretical chemistry to help guide future experiments. And it's just, all I can say is it's absolutely astonishing. Now, all of this work started to motivate space missions to Venus, but as you can see, it took a life of its own. To summarize this first part of my talk, Venus clouds, a possible habitat. The clouds have all the criteria for life. They have a liquid, a solvent, concentrated sulfuric acid, energy from the sun, and suitable temperatures. It's now an established fact that some biomolecular building blocks are stable in concentrated sulfuric acid. We have a proposed hypothesis that concentrated sulfuric acid could be a solvent for life itself. I'm now going to move on to those space missions that the laboratory work is supporting. So just so you know, there are a bunch of space missions on the books for Venus. There's the European Space Agency Envision orbiter. NASA has the Veritas orbiter and also Da Vinci, which is intended to be a parachute probe dropping down into the atmosphere of Venus. All of these missions have a lot of exciting work to do, but none of them are focused on the clouds, the cloud particles, where if we think there's life, we think it's in those cloud particles. More Venus missions are being discussed, including from India, China, South Korea. A lot of interest in Venus lately. What I'm here to talk about is something different. We call ourselves Morningstar Missions to Venus. We aim to be a series of private, public funded missions, a series of small focused missions increasing in complexity, purposely to search for signs of life or life itself. Now, I haven't said it explicitly yet, but the idea of life in the clouds is still considered crazy, taboo, and almost ridiculous by a lot of people. We're working hard to change that by showing in the laboratory that complex biomolecules can survive. Nonetheless, we need to pursue private missions because it's tough to get the community and large government agencies on board with a very risky idea. So we formed our consortium in 2020, and we came up with 3 mission concepts. From left to right, it's small mission, not very capable short term, medium mission, more capable longer term, and finally on the far right, like very futuristic, very capable, very long-term mission. I'll be talking about the first 2 missions. The first mission, we teamed up with Rocket Lab, the space company. And so our first mission is called the Rocket Lab Mission to Venus. We, myself, Yanush, and others, we're bringing the science team and science instrument. Rocket Lab is supplying the rocket, the cruise vehicle, and the probe. I'm going to now walk you through the status of this mission. On the top left, you can see the actual probe. This is the actual probe that is going to go to Venus. It's a special shape, so it can be stable as it goes down into the atmosphere. It's just going to get dropped off. It's a small, low capability mission. It has no parachute. It will slow down by its own drag in the atmosphere of Venus, spending 5 minutes in the clouds. They are opening it for you, but it will not open on Venus. It'll all be together. And what you're seeing is the probe at NASA Ames, where NASA Ames generously created and adhered the heat shield. So when the probe gets dropped off, it won't vaporize. If you look closely, you can see a little hole, this tiny hole in the probe. And through this hole, a laser will be shined through the hole. And I'm now going to move on to the right side, the top right, which is a real photograph of our instrument. We were allocated 1 kilogram by Rocket Lab, because remember, it's a small, low mass, low cost mission. And this instrument, it has a complicated name. We call it an autofluorescence nephelometer. Nephelometer means cloud measurer. We will be shining a laser through this laser port, out through the hole in the outer probe, and it will scatter off of the cloud particles. We're looking for 2 things. One is fluorescence. Just like if you go to a kid's fun house or a nightclub with the dark light, UV light, and white things light up. We're looking to light up the particles because pure concentrated sulfuric acid does not fluoresce on its own. We're looking to see that it's not pure concentrated sulfuric acid and that it may contain organic particles. Organic molecules are easy to fluoresce because many of them typically have shared electrons, especially aromatics. We're also going to measure backscattered polarized radiation. So the light will shine out, it'll bounce off the clouds back into this collecting lens. It'll scatter off a mirror so that some light can go down to the fluorescence detector. The rest will go back to split off on this polarization beam splitter cube to the 2 components of polarization. And what we're looking for is to constrain the index of refraction and particle size distribution and check it out compared to the Pioneer Venus measurements from decades past, again, to show that they're not pure concentrated sulfuric acid molecules and that there's more interesting particles there. The bottom right is some laboratory testing. And on the left, bottom left, we have taken the flight spare instrument and put it on a drone, the small light aircraft, and we have flown it around. This picture is taken in Hawaii, on the outskirts of the volcano. You may know there's this volcano that's been erupting in Hawaii like every 10 days or so on the Big Island. And there's volcanic fog that spreads out. We're not flying it right over the volcano. That is not allowed, nor would we want to, because sometimes this drone fails and crashes. And so we've flown it around and collected data to do like a blind test to see if our instrument works and if we can analyze the data. And not only that, but for systems engineering, just to show that everything works and it can communicate with us. That's the first mission to Venus, and our target launch is 2026. I can say the instrument and the flight instrument and the flight spare are ready tons of testing is ongoing, and we're really excited for this mission to launch as a demonstration that we can do small, low-cost missions with a purpose. But what we really want to do is we really want to not just find a suggestion, not just find evidence for organic molecules, but to detect specific organic molecules or classes of molecules. So we're simultaneously investing in a parachute mission. And you can see in the middle of this slide that there's a 5-meter parachute concept. And this whole parachute would be holding on to a little tiny probe, and this probe would be dropping down through the Venus atmosphere. This whole parachute system would last about an hour, half an hour to an hour in the clouds, depending on the mass of the probe and the size of the parachute. What we want to do, you can see on the bottom left, a rendering of what that would be what the parachute is holding onto. And what you're seeing at the bottom is a bunch of mini sensor patches. So this is the pressure vessel on top. On the bottom, we're calling it an aerofairing. And on this aerofairing, we want to put thousands of miniature molecular sensors. And each of these sensors would be tuned to detect a suite of target molecules, a specific class or classes of organic molecules. And these mini sensors, we're working on accelerating development of a bunch of different ones. But the one I picked to explain to you today are carbon nanotubes. And if you don't know what carbon nanotubes are, they're tiny, tiny little structures made of carbon, and they're very conductive. And here on the left, you see a cartoon of a bunch of nanotubes just kind of all line on each other, but they're very conductive. And essentially, you set them up as a circuit. So you can apply a voltage and measure the conductivity or resistivity. Now, they're very, very conductive, but if you add a defect molecule to it, so if you add a molecule onto your carbon nanotube, it changes the conductive properties. The goal is to have a target added on. So now the carbon nanotube is like a puzzle piece, and it's waiting to meet its matching puzzle piece. And when it does, molecular reactions are just electrons moving around. So it changes the conductivity. So the idea is that you design a carbon nanotube for a specific molecule, and you have lots of different specific designs. And when they match up with their puzzle piece, you measure a change in resistance. And this little chart here is just showing a laboratory experiment, not for Venus, but from a decade ago, showing you 0 through 8 different carbon nanotubes. And on the bottom, a bunch of organic molecules. And you can think of the color bar as just resistivity change. And yeah, some of them light up red, meaning that's the combination you're looking for. I just have this laboratory picture. This is not my lab, but that's myself and summer undergrad student, Eddie Hernandez. We went to visit a colleague's lab in New York City to basically see how they make these, how they put the defects on the carbon nanotube and how they measure it. And it's actually not as hard as you would think. It looks like a giant mess, but honestly, the fact that it can be done just in someone's lab is remarkable. And so we're pursuing this idea of carbon nanotube. But I want you to know that when you think of a space mission, there are over 100 steps from concept to launch. And while we're waiting to mature our molecular sensors, we wanted to take a parallel step. So we decided not to use carbon nanotube sensors. We're not ready for those yet, but just to use temperature, pressure, humidity sensors. That's what you see on the top left, these identical sensors. And the undergrad, Eddie Hernandez, got all this together, got them all to work together and operate. You can see this little box. There's his battery. There's 2 more sensors on the top right of the box. It's his microcontroller that's controlling everything and logging data. Top left, my master's student, Claire Buffington. She worked at Blue Origin for a while on parachutes. And she designed a parachute for us, one that could be scaled up to go to Venus. It's a ribbon parachute so that as it drops down and deploys, it won't shred. The air can flow through it. You can see she bought the polyester, laser cut the ribbons, and she sewed it all together with her sewing machine that she brought to the laboratory. We put all of our sensors into this box. It has a GoPro camera, I'm trying to hint where this talk is going. And guess what we did with all this?
Look up there. We have liftoff. There it goes.
Those were children at a summer camp, and they got to come out and watch us launch our weather balloon. We teamed up with the New England Amateur Weather Balloon Society. And you can see the parachute on the picture on the right, that little orange part. I'm going to play it again. I want you to look out for the parachute, the orange part. It's going to cycle back. See the parachute? It's attached to the balloon.
There it goes.
So that parachute gets launched with the payload, and the balloon is filled with hydrogen. And we've literally just launched out of a parking lot about half an hour outside of Boston, MIT. So the parachute, or the balloon rather, it's going to expand, right? As it rises, because it has to match the outside air pressure. And what's going to happen? Eventually it's going to pop. And I'm proud to say that our balloon went to 70,000 feet. And we went up to 70,000 feet. You can see the picture that our GoPro camera took before it broke. It's so cold at 70,000 feet. Remember how we were talking about that above the surface, it gets colder and colder. And at 70,000 feet, when water freezes on your electronics, it can expand and damage the electronics. Nonetheless, we got this amazing photo. And we had tracking software that tracked where our balloon was. So as soon as the balloon launched, we had to chase. There's a ham radio. They use ham radio. And the balloon has an attachment as well, beacon. And our New England weather balloon contact had an antenna on his car. So it's logging the data to an app. And we all kind of car chased this balloon. And the prediction software told us where it was going to land. So we were really excited because we had no way to transmit the data from our balloon back to Earth. We actually had to retrieve the payload and the little microcontroller with all the data. At the last moment, it looked like our balloon was going to land in a swamp. But fortunately, it landed in a tree. And we went and retrieved our box. On the bottom right, you can see the microcontroller. You can see it didn't break. It has data. It's showing you on the miniature screen. And the parachute was intact. It deployed. It reached the velocity that Claire Buffington had predicted it would reach based on drag coefficients and her model. It was a huge success. Our next step will be to send miniature molecular sensors, gas sensors most likely, repeating this amateur weather balloon experiment. We've also been exploring balloons, but I'll leave that for another time. To summarize this part of my talk, small focused planetary space missions to complement larger NASA or ESA missions is what we are trying to do. Miniature molecular sensors are a new concept that haven't yet been implemented for planetary exploration, but we expect they will simplify and redefine the way we can detect complex molecules beyond Earth. Now I'm getting to the final part of my talk, something completely unexpected. One of the singular joys of being a scientist is when you can encounter the unexpected. And I'm going to try to explain to you what happened in this story that takes us from Venus back to exoplanets. Because out of the thousands of exoplanets we know about, we have a handful of planets in the Goldilocks zone, the zone around the star where the planet is as heated by the star, not too hot, not too cold, but just right for life. However, it's extremely hard to study those planets. It's way easier to study warm planets closer to the star, planets too warm for water, and conceivably then too warm for life. I know there's another talk in this year's series on exoplanets, so hopefully they will cover this topic for you. I just want you to know that the paradigm, generally speaking, is that we need water for life. So, remember I told you that there's 100 steps from concept to launch. And for one of our mission ideas I have not talked about, we envision going to Venus and collecting the cloud particles. So getting like a reservoir of liquid from a fog collector. Just think like on a foggy day, If it's very foggy, like and about to rain, sometimes those droplets collect on your jacket. And we have a fog collector, so we imagine collecting sulfuric acid from the clouds. And in our next step, we imagine evaporating most of the sulfuric acid so we can concentrate whatever might be left over. Like if you think about going to your local river or lake or ocean and collecting water, life there is going to be diluted, very diluted. So our goal is to concentrate what would be in the droplets by evaporating excess sulfuric acid. Now, sulfuric acid has a very high boiling point. So we had to start by setting up a low pressure system. This system is not going to space. It is just the first of many steps. And former postdoc Rachna Agrawal in this picture, she's now Professor Agrawal in India at ITT Kanpur. She set up what we're showing you on the bottom right, an evaporator for sulfuric acid, a low pressure system. And what you're seeing is a glass jar, because glass is resistant to sulfuric acid, a hot plate just to heat it a little bit. And on the right, you can see the pump. Now, the only thing special about this pump is the special oil she researched to put there. In case some sulfuric acid went into the pumping system, it wouldn't destroy the oil and destroy the system. So her job was to take concentrated sulfuric acid, put material in the acid, evaporate the acid, and recover the material. Makes sense? She did all that. It all worked out until she took some molecules in the lab, amino acids, and she put them in concentrated sulfuric acid. And she evaporated the excess sulfuric acid. And no matter what she did, there was always a tiny, tiny amount of liquid left over. Her natural first assumption was that something was wrong with the equipment, even though nothing was wrong with the equipment. And I'm glad she didn't throw this out. I'll tell it to you one more time. She took some amino acids, like a white powder, dissolved it in concentrated sulfuric acid, dissolves. So now she's left with like a transparent liquid. She put that solution into the vacuum chamber and heated it, evaporated the excess sulfuric acid, but there was always a tiny bit of liquid left over no matter what she would do. And she brought it back to the team, and thank you to the team, especially Janusz Katkowski. Wow, we found out she had accidentally rediscovered a really, really special kind of liquid called an ionic liquid. These ionic liquids are absolutely spectacular. And here we're showing you a bunch of them. They're so unique because their vapor pressure is so low that they do not evaporate. It's very different from water, where if you spill water on the counter, water will evaporate eventually. If you're lazy and don't want to wipe it up, it'll go away. But these ionic liquids, they're so strongly bonded together, they don't want to evaporate. Now, just a little more detail about the ionic liquids. They are salts that are liquid below 100 degrees Celsius. So just like your table salt, they are held together by ionic bonds. There's thousands of them known in industry. And they're called green solvents because they don't evaporate. You can look these up later. They're quite well known. We didn't discover anything new here, but these are the first ones that have been claimed to be able to exist on a planetary surface. They have very low vapor pressure, like less than 10 to the minus 15 bar at 300 Kelvin in some cases. So I'm going to briefly, let me see what I've left to do here, right? Briefly explain how they form. You can, let me think for a moment. Yeah, so we're very enthusiastic about these ionic liquids because they could exist on a near airless world, like somewhere with a very thin atmosphere, or that's too warm for liquid water. These liquids could exist, and they're very biomolecule friendly. You can put DNA in them, and that is okay. Some ionic liquids, not the one I'm talking about, but different ones, have been used to try subcutaneous drug delivery. So what we're imagining is an exoplanet that on the far left started out like most planets do, we think, like really hot with lots of volcanoes and with magma, and lost a lot of its volatiles and reached a stage where it was giving off a lot of sulfuric acid from its volcano. Here on Earth, some of our volcanoes, including vents in Hawaii, are giving off sulfuric acid. They give off SO2, a tiny bit of H2O. You need one extra oxygen, but it can make concentrated sulfuric acid. And if that acid flows over existing small pockets of nitrogen-containing organics like amino acids, they literally will form an ionic liquid. And in this scenario here, we're considering warm planets close to the star that had a phase where they had sulfuric acid flowing over these deposits of organics. And eventually, once the planet settles down and reaches its mature stage, you have a very thin atmosphere, but you could still have little pockets of ionic liquid. Now, unlike water, which evaporates easily, because water evaporates easily, we need a large amount, like giant lakes or oceans. But because ionic liquids are not prone to evaporation, you can just have little tiny puddles of it. So to summarize this part of my talk, this is a brand new idea that we accidentally encountered. That ionic liquids, a kind of liquid that is biomolecule friendly, that can exist in environments where water cannot exist, can exist on planets too warm or too low pressure for water. It gives us a new possibility for habitable exoplanets. And this topic is so new, I don't have too much more to say about it, except that we're exploring it. And a year from now, we'll have enough information to give you like a giant update of how we've pursued this brand new topic. So there are very extreme environments on Earth. This is a video that postdoc Jaro Jakubiski took from Ijen, the special sulfuric acid lake in Indonesia. Our Earth is really bizarre, but what I've been talking about today are environments far more extreme than Earth. Acidities more acidic than the most acidic places on Earth. Ionic liquids, something that just exists synthetically here on Earth. But there are just so many possibilities out there in the universe. I hope that in my talk today, I've inspired you to open your mind and to think of the cases where the impossible can become reality. So to summarize, from lab to cosmos, 3 frontiers in the search for signs of life beyond Earth. 1 is the possibility for life in the clouds of Venus, which we have taken a decades-old idea and used straightforward laboratory experiments to show that complex biomolecules can exist in concentrated sulfuric acid, thus motivating a series of missions to Venus to search for signs of life or life itself. The second frontier is new miniature molecular sensors, and a concept that many people have, but we are trying to implement, to send a series of small focused missions to search for these complex organic molecules. And the third frontier is a brand new topic, a decades-old known ionic liquids, but newly cast as potential liquids on exoplanets or other bodies. That concludes my talk, and thank you so much for your attention today.
Thank you so much for your amazing lecture. I was just looking at the chat. This is why I stopped, because I realized that we have, 15, maybe even more questions. I was sure that it's gonna look like that. So thank you, and we can go to the Q&A session. We'll wait just for the banner with the question. As I know, the PNA can form the double helices. Did you try to build higher order PNA molecules simulating, like, for example, tRNA structures? And as a follow-up, but it can be crazy question, did you ever try to fit PNA into ribosome or try to build the ribosome on PNA?
We'd love to do so many complex experiments, but we're not there yet. We have, I won't say hit a wall, but we're trying to sort through some complicated things about PNA and other molecules, including peptides. One of the things you didn't ask about, but I thought I'd offer some detail, is all these molecules are protonated, which is how we end up forming the ionic liquids. And we have to understand a lot more details before we can pursue any of those ideas. But yes, we're definitely interested in some of those.
Thank you. Do you have any candidates for planets where ionic liquids could actually form? And do you think would it be possible for them to form on Venus?
I'm very impressed with the level of questions.
Thank
So
you.
we hope it might be on Venus. There's like a small possibility that beneath the clouds where it's quite hot, if some particles, the particles on Venus, they collide, they coagulate, they grow, and eventually they have to rain down. But unlike on Earth, the rain won't hit the surface. So it's possible that some of the sulfuric acid could evaporate, leaving tiny drops of ionic liquid beneath the clouds, maybe. As far as other planets go, there may be some exoplanets that are prime candidates for it. But I didn't tell you all the negatives yet. One of the negatives is that if it exists in just these small pools, it'll be very hard to detect on an exoplanet. We have taken infrared spectra. We know what some of their spectral features are. But so far, we will have candidates, but we won't have a way to detect it yet.
Thank you so much. Yes. Are possible electron donors and acceptors for hypothetical life in Venusian clouds known or at least hypothesized?
Well, we're not quite there yet, so not that I know of. But I want to just put it back out at you that we're always looking for people to work on things. You just do it on your own. And so we definitely want answers to those questions.
Biospheres and planets co-evolve, and we only have one known example of life. Should we modeling plausible biospheres and compatible life properties used to better predict what kind of biosync to look for?
That is a natural question, but it's a very tall order. Like the level of complexity to get any of that correct, it just seems so overwhelming and daunting to even think about how you would approach that. So I love the questions, but like the amount of work we're doing in the lab and like how hard it is even to make any progress at all, it's just insane. And so it would be really hard to put all that together on the biosignatures, like right from the kind of biochemicals and metabolism. So that said, we do something a bit easier. Okay, well, that's the next question. So let's ask the next question.
Yes. Are there models for chemical elements cycles that could sustain life in Venusian clouds and like similar to like our carbon or nitrogen or sulfur cycle on Earth?
There's not yet a model for this. Some people have dabbled in these models for exoplanets, trying to tie photochemistry and, possible like outgassing, in terms of vents or volcanoes from the surface. It could be time to try that on Venus. There is some work done by Jan Spacek and Steve Benner about some cycles in the atmosphere, but a lot more could be done, and I think we're ready to start that.
Yeah. Okay. Would it be feasible to use the aerogel, or would it be eaten away by sulfuric acid?
Okay, as far as I remember, and I have a very bad memory, it would be eaten away by sulfuric acid. But,
Okay.
There's always room to revisit old ideas.
If life does exist on Venus, what's more likely? Had it evolved on the surface long ago and then run away into the clouds, or emerge in the clouds in the first place?
I do want to say thanks to Janusz Petkowski, we leave no stone unturned. And we definitely read all about this and try to hypothesize, but it's honestly more speculation at this point. So most people think that Venus, like Earth, was born with water oceans. But at some point it had a tipping point and got too hot and the water oceans boiled away and evaporated. But if it did have water oceans, sure, we could imagine that it formed in the water oceans and evolved to the clouds and maybe evolved eventually to live in the clouds. But honestly, that'd have to be a lot of evolution, because remember, our DNA can't survive and it would have to like self-generate, like swapping out parts, a whole new kind of DNA. Some people now don't think Venus ever had liquid water. They think Venus was always too hot. And the point of contention is the cloud models, like just people don't know if it was always too warm to have a water ocean. In that case, if there's life in the clouds, it had to form in the clouds somehow. And there are some ideas there about wet, dry cycles and the like, but either way, we're mostly just speculating at this point.
Taking into account presence of the concentrated sulfuric acid and relatively short lifetime of organic compounds in the context of origin of and evolution of life, are there any candidates beside PNA?
Well, there aren't.
Sorry, here is the continuation. For compounds that can for other structures important for life, like membrane or other compartmentalization catalyst equivalents for enzymes.
Okay, so far for most of that, I'm sure there are. I just want to speculate and say I'm sure there have to be. We don't know about them yet. But there are probably all of the above, in fact. There's no reason why there shouldn't be. One of our team members, Daniel Dusevic, has worked on lipids with polar heads for membrane formation and has successfully formed tiny vesicles in concentrated sulfuric acid up to about 90% concentrated sulfuric acid, the rest water, and has shown, that they do form it. So probably all of those above. In practice, we've only shown one category of those so far.
Mm-hmm. Could half-life kind of life might exist in ionic liquids? Any growth tests or extremophiles?
The ionic liquids that we've worked with so far are way too extreme for our life, even though our DNA might be stable in it. We definitely put a life form in it. It's a great question, right? Because if you have a lab, you can just, put something in it. It didn't survive at all. To answer this question, don't know the answer to that.
Mm-hmm. And probably last question.
I do want to say that I doubt that any of our life could survive in any ionic liquid we can think about right now. Mm-hmm. So we're just back to some of the earlier questions about enzymes or lipids or other kinds of molecules, not like whole life forms yet.
And the last question, do you have any...
we answered this one already.
We answered this question. Yes, like you answered, sorry.
Right.
But there was, I think, the last about the clouds. Okay, so I can ask by myself. It's a question about the simulating the Venusian clouds. Is it possible to simulate them on Earth, including the layers, for example, that you can have, I don't know, like a cube with different layers simulating the Venusian atmosphere?
Well, people simulate the clouds themselves. There's data from Pioneer Venus that tells us the cloud particle size distribution and roughly composition as a function of altitude. So people have models of clouds, yes, layer by layer, where they have to have like nucleation, and growth and particles setting out, and all of that has to match the current data. So there are definitely models, but it's mostly physics-based and less chemistry.
Mm-hmm. Mm-hmm. Okay, I think I have a thing that was the last question. So one more time, thank you so much for an amazing lecture, and good luck with your future research.
Thank you very much.
Thank you.